hello, everyone. Thank you for joining the panel today. I'd like to introduce myself. My name is James DiFrancesco, and I'm the Director of Optical Astronomy at the Hertzberg Astronomy and Astrophysics Research Center of the National Research Council of Canada. We're pleased today to bring you a panel called From Nebulae to New Markets, Leveraging Canadian Astronomy for Innovation. This should be a very interesting and exciting panel. Astronomy is itself an interesting and exciting science, but we, of course, also do it not just for its own sake, but also to provide, to spark innovation within Canada to meet the challenges. Before we begin, I would like to again welcome everyone to the pre-sessions of the Canadian Science Policy Conference, which will begin next week. These conferences are very interesting, and we hope that you will be able to learn much from the various sessions that are going to be occurring both, well, this week and next week. In addition, I would like to describe a land acknowledgement. Hopefully you can see that here. I'm coming to you today from Victoria, British Columbia, which is on Vancouver Island. And we say this acknowledgement at the beginning of all of our meetings. We acknowledge that we're meeting today on the traditional territories of the Coast Salish and the Lekwungen-speaking people here on Vancouver Island, who are the custodians of the respective lands and waters. These areas have long been the gathering places of the First Nations, well before the arrivals of the Europeans. And we are grateful for the opportunity to live, work, collaborate, and learn here and respect the continued connections with the past, present, and future, and the ongoing relationships with Indigenous and other peoples in the British Columbia community. So we invite all attendees today to reflect on the relationships that you have to the communities that inhabit this land and share the night sky and wonder. Okay, so today's panel is going to be discussing Canadian astronomy, but we have decided to focus it specifically on the topic of space astronomy. Space astronomy is, as you can imagine, a relatively new slant on astronomy, but it has quickly become a focus for astronomy worldwide. There are many benefits to going into space, not the least of which is that we're incrementally closer to the objects that we study. Astronomy has really benefited from access to space. We thought it would be a very interesting panel to focus specifically on the aspects of space and in astronomy and innovation. You can see the benefits to space astronomy quite plainly by looking at the wonderful images from the Hubble Space Telescope that have been produced over the past 30 years. It's actually quite striking to look at a textbook from, say, the 1980s to a modern textbook to see the great leap in the fidelity of the images that we are now able to see commonplace thanks to the Hubble Space Telescope and other observatories that have launched since. This is just a breathtaking image of a star cluster, and you can just see how incredibly sharp and beautiful the images that we see from Hubble are. This is because satellites like Hubble are able to be above the Earth's atmosphere, which causes blurring and distortions, and giving us the crispest views of the universe that we can achieve. Hubble, of course, images in the optical regime in the so-called visible window of wavelengths. Yet things in the universe radiate at a whole host of wavelengths. And our narrow view can be restricted if we only look at things in the so-called visible window that our eyes can see. And this chart shows, or this plot shows, how difficult it actually can be to observe outside of the so-called visible window. And you can see that at wavelengths shorter than the visible window, say in the ultraviolet and in the X-ray, the atmosphere makes it completely impossible for us to access those wavelengths from the ground due to ozone and molecular oxygen in our atmosphere. So to see those wavelengths, we have to go beyond the atmosphere to see them. And then likewise, on the other side of the visible window, we have the province of the infrared. And there, water and carbon dioxide produce a scattering of narrow windows that allow some access, but some areas are just, again, completely opaque, say here at around 0.1 millimeter or so wavelength. And these really have otherwise restricted our view of the universe, but again, going beyond the atmosphere allows us to access them completely. This is actually a marvelous image that was released this morning. I guess in recognition of today being Halloween, NASA launched this very spooky image, put out this very spooky image of a supernova remnant, combining data from its venerable Chandra X-ray observatory and its relatively new imaging X-ray polarimetry explorer. This spooky hand reaching towards what I hope is a piece of candy is actually a supernova remnant, and that white object in the middle is a ultra-dense compact remnant of a once massive star called a pulsar that is lighting up the region with a wind and causing it to brighten up in X-rays. We could not see something like this from the ground at all. Now, my own career has been largely entwined with space astronomy. This shows some lovely images from the Spitzer Space Telescope of a star-forming region that I myself have studied quite extensively. And by going into the infrared, we can actually see the cold and dark creches from which young stars form and emerge from their host molecular clouds. And those red bright points that you see are in fact the new generation of stars emerging into the galaxy from this cloud. This was a near infrared image and was part of a very successful mission. I was also involved in a European mission called the Herschel Space Observatory, and this shows the much larger view of that cloud. This here, where I'm circling the cursor, is the area that Spitzer imaged before. And by going to longer wavelengths, again, these could not be seen from the ground at all. You can actually see the ghostly wisps of filaments out of which form the dense gas out of which more stars will form in the future. So going into space really does give us this incredible complementary view by letting us look at the universe in new and different ways. Of course, now we have the James Webb Space Telescope, which is producing images like this, which is also of the Ophiuchus star-forming region, again, in the very central part of the images that I showed before. And James Webb, of course, is the most exciting new telescope to have been launched by NASA. Canadians are involved in that very, very closely. And this shows a small cluster of young stars that are forming out of this very dark patch. This lovely yellow region is lit up by this young star here, shining around the dense gas that it has cleared. And you can see here the dark red ribbons of gas being expelled by a young star as it continues to accrete gas from its surroundings. So it's images like this that really help us learn more about the universe, and space astronomy has allowed us to do it. So in this panel, I would very much like to you to learn more about how Canadians are involved in space astronomy, how it benefits both our understanding of the universe as well as our industries, and as well how Canadians themselves have been quite at the forefront globally in exploring the universe using many of the various astronomical telescopes that have been launched in space, of which Canada has been partnered in many. So with that, I would like to end with this lovely image of NGC 3324, one of the first images that Webb has released last year. This spectacular image was only a small part of a very large region. Is one that's very dear to my heart because my graduate student and I have submitted a paper describing the young stellar star population of this region. And it's having access to data like these through things like Canadian storages of Webb data, like we do at the National Research Council, really enables us to share in this discovery of the universe, thanks to telescopes like Webb. So with that, I'm going to stop sharing my screen, if I can, and I'm going to move on to introduce our various panelists today. I need to please find the correct window. Okay, so we are going to have brief introductions from our three panelists today. We have Sarah Gallagher, who is the president of the Canadian Astronomical Society. She's also the director of the Earth and Space Exploration Institute at Western University. Thank you, Sarah, for coming today. And before you begin, I just want to quickly introduce the others. We also have Frédéric Grandmont, who is the from the company AB&B, or ABB, sorry. And he is very much involved in the industrial side of providing access to the universe through astronomy. And then lastly, we have Joshua Montgomery, who is at McGill University. Joshua is a postdoc there, and he is also the president of TO Technologies. Hope I got that right. And he is involved in many projects, both on the ground and in space, providing key instrumentation to allow those to work. So we're going to go through each of our panelists, who will provide a brief introduction to the topic, and then we will move on to a moderated discussion section where we will each discuss a series of questions that we have prepared for you today. And then after that, we will have an opportunity for you to provide questions of your own through a Q&A. We would like to invite you to submit questions to the panel beforehand using the chat box on this Zoom call. So moving forward, let's hear a little bit first from Sarah, then Frédéric, and then Joshua. So please introduce yourself, Sarah.
Thank you very much, James. It's my pleasure to be here. As you said, I'm at Western University, where I'm a professor in physics and astronomy, and I'm also the director of the Institute for Earth and Space Exploration. Several years ago, starting in 2018 to 2022, I was also the science advisor to the Canadian Space Agency, where I had the opportunity to sit on the executive and advise the executive on science investments, which included space astronomy, as well as other space science fields. So that was a great privilege, but now I'm back to my full-time job at the university, and I'm also the president of the Canadian Astronomical Society. So I just wanted to highlight a couple of things that James mentioned, and then also just explain why astronomy and space astronomy can be such an engine for innovation, particularly in the Canadian context. So one of the things that is unique about astronomy, as James mentioned, there's specific reasons for us to go to space. So there are things we cannot study unless we go to space, because the atmosphere gets in the way. And also, once we get above the atmosphere, we can take much clearer pictures, which allows us to get a lot more detail. So we have clear scientific reasons for going into space. But space is hard and space is expensive. So when we have an opportunity to go into space, we want to do really awesome things. We want to actually take things to the next level. And examples like the James Webb Space Telescope absolutely do that. So there's some ways in which the James Webb Space Telescope is 1,000,000 times better than the Hubble Space Telescope. And so that really allows us to take our science absolutely to the next level. And that ambition requires basically new tools, brand new tools. So the science can really push the technology in a way that can be very, very exciting. And Frédéric can elaborate on how this actually plays out within his context, as well as Joshua. But it's something that the science can really push the technology in a way that's quite exciting. The other thing is, because these projects are expensive and hard, they're often international. So the James Webb Space Telescope, again, as an example, is an international collaboration. So it is led by NASA in the US, there is participation from the European Space Agency, and Canada, the Canadian Space Agency, also contributed 2 of the instruments. And so the advantage of that is, first of all, you're sharing the cost of something that's very expensive, but you're also bringing in the science communities from all of those different countries in order to participate in maximizing the science return and getting the most science out of everything. So the international scope of big science projects is very typical, and astronomers are used to working in that context where we have collaborators around the world and in all the time zones, which can make meetings challenging, but that's pretty normal for the way that we operate. So we automatically have a collaborative and also international focus to a lot of our teams. And we are fortunate. I'm so proud to be an astronomer in Canada. We are really good. And so as the president of the Canadian Astronomical Society, I am very proud of our community. We are excellent. We are recognized internationally as being excellent. And so people want to have us on their teams. But we are a relatively small community. And so we have to choose where are we going to invest our efforts and what are our priorities. And so we have a process, which again is unusual in Canada, of defining our priorities. And it's called the long range plan. So every decade, with the support of the National Research Council and the Canadian Space Agency and the Canadian Astronomical Society, as well as the Association for Canadian Universities with Research in Astronomy, we undergo this long process of defining what our priorities are. It's called the long range plan. The output is a document about this thick in 2 languages, both, and that defines our priorities through a collaborative, consensus-driven process. It takes about a year in order to do that, but then we come to a decision about what our priorities are, and then with our international and industrial partners, our goals are then to achieve those priorities. And so right now, our key priority that we're advocating for is CASTOR, which is an ultraviolet space telescope that takes large pictures of the sky. So the pictures of CASTOR are about 100 times larger than the pictures of the Hubble Space Telescope. And that allows us to study all sorts of amazing things. So growing supermassive black holes and hot young stars, and to learn insights into the atmospheres of exoplanets that you can't learn in any other way. And so Canada has an opportunity to lead a major space astronomy project for the first time with this CASTOR telescope. And that's what my job as the president of the Canadian Astronomical Society is, to advocate for this investment, which is very exciting. We already have international partners that are interested, including the UK, France, Spain, and South Korea. And this will give us an opportunity to be on par with the European Space Agency and NASA with these wide field imagers, and where we would be making the unique contribution in the ultraviolet. So that is, I'm going to stop there and pass it off to Fred. Thank you.
Hi, can you hear me? I guess so. So I hope you see my screen. I'm just going to do a short presentation of who is ABB. I like to joke about the fact that I'm an astronomer turned to the dark side. Instead of continuing on to research, I turned it into the industrial field. But I take great pride, and I really enjoyed the type of work I'm doing, because we're providing the tools that allows for these unique discoveries, which can be on the ground or in space. So I'm just going to do a short review of what ABB is. So just next slide, just a second. Yes. So ABB is a big multinational company headquartered in Switzerland, with presence in about 100 countries. But they happen to have a group that is specialized in automation and measurement and analytics, which have many factories around the world. And in Quebec City, we happen to be one of these R&D sites for the global ABB measurement and analytics. Our site was originally a startup company founded in Quebec City by 2 PhD students from Canada that ended up being acquired by ABB. But we are now a recognized leader in measurement solution for industrial processes monitoring. So we help a lot industries to automate processes, can be for pharmaceutical industry, control the active ingredients inside pills, or it could be control the octane level in the gasoline you buy at the gas station. But we also carry rich heritage into doing optical system, custom optical system, in which respect we are some sort of a contractor, just like an engineering firm would bid on, let's say, a bridge construction. Well, we will put up together a proposal to build, fancy instruments that are very custom and designed to achieve a certain type of measurement. And in this respect, we are, one, if not the leading company in Canada for responding to such requests for proposal from either the Canadian Space Agency or the defense sector, for instance. We have quite large manufacturing infrastructure and about 190 engineer technicians in our R&D group, which makes us the largest R&D group worldwide for ABB into the process automation and measurement analytics. This is just a short summary of our heritage. Canada was the spark, the Canadian Space Agency, namely, was the spark to our introduction into the space sector with calibration source that we did for NASA telescope on Terra. The instrument, the Canadian instrument, was called MOPIT. And then we were awarded a complete instrument on the SciSat, which is the spectrometer that flies in orbit with the most detailed view of the atmosphere. We probe 70 molecules and isotopologues for about 20 years now. The satellite is still active, working very well. And from these successes, we were able to export our know-how into a number of other opportunities that were pure exports of HQP, labor effort. The space industry is really labor intensive. We spend thousands and thousands of hours designing the new system and testing them and make sure they will resist the launch vibrations and the vacuum of space and things like that. But so we had a very great success in applying this know-how and growing from that. And we basically sold equipment just about anywhere in the world. And today we are making further growth with the arrival of the private sector in the space industry. So not only do we respond to government RFP now, but we also respond to the private company RFP. A good example being the Montreal-based GHGSat company, who is the first one to make measurement from orbit of emission. So you basically, with such an instrument, can measure any site on the Earth, any site that will emit a fair amount of greenhouse gas. You can have an independent reading and assessment of what it is that they're emitting, regardless of jurisdictions or access to airspace, because we operate from space. And that's an immense advantage in being able to operate from space. We have a rich heritage in producing instruments for astronomy. This is an example of one that's dear to my heart because it's an instrument that follows somewhat in the footstep of my PhD thesis at Laval University. This instrument was installed on the Canada-France-Hawaii telescope in 2015, and it continues to produce these very nice image of extended source like you see on the right. It's a camera that extracts a spectrum for any of the 4 million pixel that is there. There are interesting videos on YouTube about this, and it's pretty unique Canadian niche technology, I would say, in the zoo of instruments that you can see in the field. We even have requests recently for, studying a concept for putting an instrument like that in space. So that's all very enthusiastic for the people that work on such endeavor. We also contributed equipment for other high-profile astronomy mission. The successor, not really the direct successor to the James Webb, but let's say NASA does a very large flagship astronomy mission every 10 years. The one that will follow the James Webb is called the Roman Space Telescope. It will be launched, tentatively in 2027, and it will be equipped with a coronagraph. A coronagraph is a device that allows to block the light from a star in order to reveal the light from closely orbiting object, namely planet in this case. And the objective of our camera is to collect this very, very faint light from these exoplanets and potentially reveal the spectrum of these planets, just like we would do when we observe the Earth at a large distance. And by analyzing the light content of these planets, these exoplanets, we could very well reveal the presence of life on the exoplanet. And I mean, this would be a historically or in the history of humanity, a big milestone, you know, having a confirmation that there is life elsewhere. It's been tough to make that proof on Mars, but it's, well, many people believe we will be in a position to make that demonstration in, you know, in the next decades or so, and that will be with instruments like that. So that's something we're very proud of. Another example is Canada has embarked in a big, ambitious project. This one from the ground, the 30-meter telescope. It is in some sort of replanning at the moment, but we are helping, let's say, the NRC, the Canadian government, with providing subsystem for the Canadian contribution to this, you know, magnificent landmark objective. So these bring very interesting project for our engineers, and they really consist in provide attractive an attraction power for hiring new staff and getting people motivated, and no, not thinking that they would have to go to United States or NASA to work on these crazy space project. You know, you can do that directly from Canada. So there's nothing to be shy of being in this country. That's it for now. I'll just stop sharing. And I think I'll pass it along to Joshua.
Yep, thanks, Fred. Hi, everybody. So as James said, my name's Joshua. I'm a postdoctoral researcher at McGill and also the co-founder of a technology company. And my role here is in some ways a bit of a case study in the way that Canada's been able to make really specific investments into pieces of technology for science and leverage that into an outsized role in the scientific community and the global community, and eventually sort of translate that into industry and back into other benefits beyond astrophysics. So I'm going to out myself right here at the top as actually being a bit of a transplant. I'm American. I came to Canada about 10 years ago. And before I came to Canada, I was working in high energy particle physics. And I became enamored with the sort of observatories, telescopes, science that's done in really harsh conditions, in extreme environments like the stratosphere or the South Pole or the Atacama Plateau in small groups. And so I kind of zeroed in on changing my field of research to find some way to work in that environment. And pretty quickly, CMB astronomy, so microwave astronomy, filtered up to the top of that. And almost every microwave astronomy survey instrument on Earth uses technology developed in Canada, in one of two places in Canada. And so it was pretty clear immediately that if I wanted to work in these environments on this technology, and I wanted to do it in kind of a science engineering instrumentation-y way, where I had to learn detector physics, read out, and then actually do the science at the end of it, Canada was the place to be. And I started working at McGill with Matt Dobbs a little over 10 years ago, specifically to start at the South Pole, which is behind me here, at the South Pole Telescope on a stratospheric balloon project called EBEX in the Atacama Plateau in Chile on Polar Bear 2. And then eventually you can kind of see where this is all building. All of these are efforts to try to defeat the atmosphere in some way. You're either trying to get above it in the Atacama Plateau, or you're trying to go somewhere where it's really dry and really cool. And we're clearly iterating towards getting to space. And so while I was a graduate student, I had the opportunity to start working with the Canadian Space Agency, which recognized Canada already had this leading position in the world in this very specific thing that was readout technology for superconducting detectors for microwave astronomy, and said, okay, listen, if we're really good at this terrestrially, clearly we should be leading the world in this for space-based projects as well. And that started 10 years of development on and off with the space agency and with other international collaborations to develop technology that would become the baseline hardware for the Lightbird Space Observatory, which is going to be the first space observatory that has these particular kind of sensors. So that launch date is 2030. And in some ways, as an academic, I've been continuing to work on the technology piece of this, make this all possible. But while I've been doing that, it's also been clear that the technology that we've been developing for astronomy has matured to the point where, first of all, a lot more astronomers want it. More opportunities for these telescopes to go up around the world, more opportunities to expand, whether we're looking at microwave, infrared, terahertz. But also there are other applications, and those applications aren't necessarily suitable for a university to develop. And so it became clear that there was an opportunity here to take a lot of that know-how, move it into a company, continue to work with scientific experiments and scientific projects, but also take all of that development work and industrialize it and make it available to the larger sort of economic world and industrial world. And we had an inkling that we would continue to have potential sort of customers, if you'd say, in the scientific world. What we didn't realize is that there are all of these other possibilities for this technology, and just by moving it out of a university into a company and starting to explore that with industrial partners, it became clear that there were people interested in pursuing it. So that's become something that in the last year or so we've been working a lot on with other Government of Canada agencies for space domain awareness, to look at satellites in orbit, for radio correlators for either radar or for astronomy, and for medical physics, to look at terahertz imaging. So the same technology that we need to make a telescope can also be used to make a microscope. And the kind of thread that wraps through all of this is support from Canadian policy making and Canadian government initiatives. So even going to launching the company T0 Technology, that was only really possible because of policy initiatives that make things like MyTax possible, which allows postdoctoral scholars like myself to pursue starting a company in addition to and in parallel to their research. So I kind of want to tie it up there and pass it on. I'm looking forward to the discussion section, but I think that there's a lot of opportunity for very focused policy decisions that we make in Canada to yield these outsized returns, like being the de facto control technology over a huge portion of the globe's telescopes, to being the de facto provider of this technology from an industrial context. And one of the things that this does is it lowers the cost and the barrier of entry for other scientists. Okay, thanks. Back to you, James.
Thank you very much, Joshua. Very much appreciated. And thank you to all the panelists for their presentations. So now we move into the moderated discussion portion of our panel. I would like to pose questions to our panelists, engage in conversation. And I would also like the participants who are joining us as well to think about questions that they would like to ask later on in our Q&A session. So first, I would like to ask Sarah Gallagher, who is not only the director of that Institute for Earth and Space Exploration in Western University, as well as the president of the Canadian Astronomical Society, but also a professor of the Department of Physics and Astronomy at Western, who has been here in the Canadian community for about 20 years now. I'd like to ask, given your experience, Sarah, what is the process for a successful space astronomy mission in Canada, from the ideation, the very first thoughts about what can be done, to its actual operations? Can you briefly describe that? I will invite the other panelists to chime in as well.
Sure. Thanks for the question, James. So the process is pretty similar, regardless of what the scale of the project is, but the timeline for the process gets correspondingly longer as the project gets bigger. And in general, when we're starting with a project within astronomy, we are science driven. So what is the question that we cannot answer right now with the available technologies that we have. And that is the start of a conversation when we say, what are the big questions that we want to answer? So as an example, for the James Webb Space Telescope, I mean, one of the leading science drivers for that is, what do the very first galaxies look like? And so that science question drives you to, well, we need a really big telescope because those first galaxies are really faint. And we need that telescope to be sensitive in the infrared because that's the light that is emitted by those telescopes. And by those galaxies. And so those are two of the engineering requirements that are driven by the science question. So you start with the science question, and what happens is you have a back and forth between the science questions and the requirements by the science and the reality of actually building something that is cost effective and physically possible. So the engineering and the science really have to go in tandem. And it's often the case that there are lots of great ideas that get started, but you hit some sort of an impasse. And maybe the impasse is because you don't have the international partners you need, or the technology is too immature and it needs to be advanced. Or things are just going to be too expensive. So there's a lot of ideas that people have that start percolating that don't actually advance to the process where you have a concrete design that can advance. And so we have a formal process in space where we talk about phase 0, phase A, and where you start with the initial concept where you're thinking about what you want to do, you're driven by your science questions, and then your engineering design gets more and more mature as you go through the different phases, but you always want to have that close relationship between the science requirements and the reality of what's possible with the engineering. And if we talk about some projects, if we have a small telescope, for example, a microsatellite, which literally could be this big, that might be something that could be realized in a couple of years. But when we're talking about something like the James Webb Space Telescope, that's a generational project. That is effectively someone's entire career could be involved in doing a big project like that. So we are used to thinking in long term and also being incredibly ambitious, because we don't want the projects when they finally get realized to be irrelevant or out of date. And so you have to have those you have the steps that you need along the way, but you generally have your big picture. So I think I'll stop there and give my fellow panelists an opportunity to weigh in.
Yeah, maybe if I can, Sarah, you use the word ambitious. I think within the different science community or user community that we serve in the space business, that's certainly an objective that does characterize the astronomical community. They're very ambitious. They don't fear the challenge. James Webb, I like to present James Webb as the modern equivalent of cathedral. When you look at these European cathedral, you're like overwhelmed by the effort and amount of work because you can see it. But James Webb is essentially a modern version of that. I mean, there's an incredible amount of work that goes into such a telescope. Just the sheer budget of these endeavor, I mean, talking close to $10 billion. There's not a whole lot of space missions that are on that level. So they're really, really pushing the boundaries of technology. I think you can be assured that there is no such space telescope, even in the military, to look down on the Earth. It's really the astronomer that pushes the boundary. And then probably other sector that reuse, the advancement that were made. I can take an example, for instance, your modern weather forecasting nowadays is done mostly by supercomputer that are crunching a digital model of the Earth atmosphere that gets refreshed, several times per day. And we use instruments similar to those that were flown on the James Webb to observe the Earth. But when we shop for detectors for a customer that wants to do an instrument like that, we will tap on the same supplier that have been providing technology for the James Webb, but it will always be a level of technology that's a little less, I would say. James Webb being like their expression of capability, like we've done James Webb, so we could do your project. You know, we push our technology that far into these missions. So it's really a field that pushes out the technology. But they're risk taker. They accept to take risks, basically.
Okay, thank you,
I
Fred.
think one of the things that you framed that implicitly with James was thinking about what are the risks of running, being the lead on a large project. And I think that, you know, another way to think about it is what are the risks that you're able to avoid, to sidestep, to retire by being the country that is doing the lead. I mean, we spend so much of our time on projects with international collaborators, where there are a lot of risks associated with providing, you know, a small important tool on a large mission. We're changing the paradigm a bit by trying to go after something like Castor, where we're the lead. And I don't know the answer to this, but I imagine that that there are a number of risks that we're actually retiring by taking on that responsibility that Sarah might be able to speak to.
Yeah, just to follow up with what Joshua said, one of the early, and also to round out your question, James, one of the things that happens in the early processes of defining a space mission, especially a big ambitious one where you're really taking on, you know, a brand new, trying to develop a brand new capability, is there are technical risks that that you do want to retire early in a project. So if you're not exactly sure that your detector is going to be able to do what you want to do, then you want to try to solve some of those technical problems early on so that you can retire those risks that Joshua mentioned. And so, for example, with the Castor Space Telescope, there's been a 15-year investment by the Canadian Space Agency in developing both the science case and retiring a number of the technical risks. So there's technologies that were quite immature when it started, where now they have advanced to a point where they're much more trustworthy, and it's reasonable to think that they could be, that this telescope could be built in a 6-year timescale once the funding comes through. So that is a very intentional and deliberate process in the course of making these big. I mean, nobody lightly spends hundreds of millions or billions of dollars. They do it in a very careful, deliberative way. And certainly one of those big technical risks, you want to try to retire them early in the process so that you know you can count on it and that technology will be there.
Okay, thank you, Sarah. So just to elaborate on this point a little bit more, what is the role of, say, the Canadian Astronomical Society in developing these projects and in finding the kind of consensus that is necessary for investment in these projects, either large or small?
So the role of the Canadian Astronomical Society, which we call CASCA for short, is not to tell the astronomy community what we're going to do, but to ask. And so I mentioned the long range plan. It's a year-long process. And that starts with a number of people. There's a solicitation for white papers. So different groups within the community say, hey, I think this is the next greatest thing that we should invest in. And so those were submitted. I believe there were 70 that were submitted in the last long range planning exercise. So it's a very collaborative. And so anybody can submit something and say this is the greatest thing. And so there's a committee, they read all of those. There are town halls, there's events that are associated with our annual meetings. There are levels of drafts that get written and circulated for feedback. So it's and we do this in conjunction also with our partners. So industrial partners, the National Research Council, the Canadian Space Agency, the organization where all the universities are a part of. They're all stakeholders in this whole process. So it also depends on where the initiative is. So someone like Joshua, I mean, he's obviously very passionate about coming up with fantastic tools for microwave astronomy. And so you have to be responsive and also you have to make room for the new people who are coming into Canada. So it is a very I came from the US originally, and I am so thrilled to be here and to be able to participate actively in this community. It's exciting. It's dynamic, it's agile, and you have an opportunity also as a relatively newcomer to Canada to actually be involved in these exciting projects in a leadership role. And that's something that's really attractive.
Hey, thank you, Sarah. So I'd like to actually probe a little bit more on the connection with industry, with Frederick and Josh. I mean, what is the process by which a scientist engages in industry to determine whether capacity exists in Canada to realize their scientific goals? I mean, there's a certain dance involved where people have ideas, but what is the process by which those sorts of things are discussed?
Well, that's an interesting process because there is really cross-pollination between the two type of expertise. Scientists that move on to the industry side, people from industry that are at the Canadian Space Agency. We basically meet in international conferences where we discuss these ideas, and people write paper about capacity of a recent instrument. Somebody will write a paper about a new type of detector, and then a scientist will come to us and say, what if I combine that detector with that other technology piece that was done by another group? Do you think we could make that kind of measurement? And then we'll run a back of the envelope calculation and say, yeah, this looks promising. How much do you think this would cost? And you provide some rough order of magnitude number, and then boom, an idea gets started. Sometimes it's very intricate. We have I'm going to use an example. It's not necessarily exactly astronomy, but we make an instrument that measure methane leaks on a drone, on pipeline. And I just happened to be with a Canadian scientist and talk about that technology. And he's saying, oh, that's interesting because we have recent proof that there is potentially methane on the surface of Mars at a very, very low concentration. And it's a puzzle as to why there is methane. Usually methane is a molecule that will disappear within about 10 or 100 years. And because Mars is not geologically active, we don't expect to find some. So they're very curious. Could it be, biological element in the underground? So just out of that conversation, we put up a proposal to the space agency, and now we have a potential mission cooking, and we received some R&D money from the Canadian Space Agency to make an instrument that's tuned for Mars. And maybe in 10 years from now, this will turn into an instrument on a rover that will prove that there is life on the Martian underground.
Cool. Very cool. So do you have anything to add, Joshua?
Yeah, I mean, so on our side is there are a couple of things that we look for in the scientific community, and it's a little bit easier when it's a field that you're already pretty well embedded in. But as as technology is being developed and it's all very emergent, everybody's doing something that's quite different from the next person. And all of that slowly starts to converge, and it converges through a number of different organizations and institutes doing their own work that's all sort of partially orthogonal, and that's good. That's how good science happens and good technology development happens. But then at some point, you notice that everybody's reinventing the same wheels. We've converged at an answer that is 98% right. And there's still a lot of ground to be gained in science, in astrophysics in particular, to get that last 1 or 2% or squeeze that last percentage. But by the time we've all kind of gotten to the 98% consensus level, it's clear that this technology is, first of all, mature enough that it's probably useful outside of astronomy, and B, is now costing astronomers and scientists more money, effort, and time to reinvent that wheel than is necessary. Then it can become something that is, commodified is not quite the right term, but can be moved out of science and into engineering, and then be offered as a tool to apply a lever to that scientific investigation rather than be the thing that holds it all up. So we've seen that happen with readout for these superconducting detectors, where in general, if the astrophysicists want something that's like 5 nines complete, but it's all turnkey and you can start to build this and provide it, and you have a lot of conversations where people are like, man, I wish that there was somewhere I could go to just get this box instead of having to reinvent it every single time that we propose for a new telescope. Then it's time to make the box. And then the next sort of key there is being able to turn around and say, okay, well, we've got this thing that's 5 nines correct for astrophysics, but somebody else who was interested in terahertz imaging or imaging satellites is a really good example. And we've spent decades in astrophysics seeing satellites as foregrounds. And especially in the microwave, where the atmosphere is pretty transparent and where the satellites are pretty bright, we actually go to lengths to remove the satellites from our data. So we know that our technology is very sensitive enough to see the satellites, not a problem. Astronomers want it to be a lot more sensitive than that. But if your goal is to track those satellites, we're already done, we're already there, and it's time to just take that technology and move it outside of academia. So in that way, a lot of the conversation that's happening is, using not necessarily industry as a flag for what's ready to be consumed, but using the scientists as an indication of like, where have we already converged? Where are we retracing our own steps instead of breaking new ground? Now let's move that out.
Okay, thank you very much. Okay, so the next question I'd like to ask, and I'd like to direct it to Fred, as the Technology and Business Development Manager for ABB. What do you feel is the attraction of space astronomy for developing and retaining highly qualified personnel in Canada?
Well, first of all, most of our staff that works on these missions are not necessarily from an astronomy background. It can be mechanical engineer, it can be software, electronic, but a lot of the, if you follow the cursus of these individuals, what brought them to STEM career, like mathematics, engineering, and so on, they had some interest in the high profile science questions and things like that. In most cases, if not all cases, they really feel they're happy about contributing to big questions, and even though you're not the scientist processing the data and having your name on the paper, but sometimes they do have their name on some of the technology paper we publish, which is also a good thing they appreciate. But even though they're not the one publishing the science, they really get the feeling that if it wasn't for their work, because you face many kinds of really critical challenges. Sometimes the thing just doesn't work. It breaks on the launch vibration, and you have to, find a solution. And when you actually find solution, make it work. And the instrument starts in space. You really feel the astronomer could do that discovery because of you, because of your work, and that's very motivating. I mean, it's not your, it's an unusual job, I could say.
Pretty cool. Okay, do you have anything that you would like to add to that, Joshua?
No, I think Fred hit the nail on the head. I mean, that's true for me as well. Like, that's why I ended up here, was trying to chase that unusual job and trying to chase something that feels valuable. And at the time, doing that in academia seemed like the obvious choice, because that's where the experiments were. I found that again in industry now, in kind of the same way, but it's still very closely tied to following the scientists, following the astronomers, being able to tee off technology and applications where we see it into industry to further it, but staying closely aligned with where the cutting edge is, in part because of that excitement. It helps us with recruiting for sure, and it helps with just motivation, creativity, all of this.
Okay, thanks, Joshua. So Sarah, anything you'd like to add on sort of the academic side to that question?
Yes. So I think a lot of us, I think, had similar training. So in terms of where we started, so we started in graduate school and in universities, and what we specifically studied was different, but that was sort of an environment that we were familiar with and that we came out of. And I find with my students, a lot of them see what the life of a professor is like, and that may not be something they're super excited about, either because they don't like to teach, which is totally valid. I like to teach, so it's a good thing I'm in a university, but not everybody does. Also, people are motivated by different things. And so people are motivated by the big science questions where they want to be there or to contribute to the big science questions. And one of the staff member I have at the Institute for Earth and Space Exploration is a planetary scientist who functions as one of the roles that he has in our institute is he's a project manager and he helps write proposals. He's a research officer. And so he loves to be participating in the research enterprise, but he doesn't want to be the principal investigator of a project. And so I think that's one thing that, you know, that we don't often think about. All the people who enable these things to happen, they're not all scientists leading the project. They're all sorts of different people. But a lot of these people are motivated by the science, it's exciting to them, or they're motivated by the challenge. And so when you have smart, talented people, they want to do hard stuff because easy stuff is boring. And so that is a major motivator as well.
Yeah, maybe I could add to that, being in my position or the industry position, we are touching on a number of science field, not just one. Let's say you're the expert in, I don't know, nebula. Well, you're the expert on nebula and that's your field. We are providing instrument for people doing global warming analysis, astronomy, detection of transient object. It's very diverse, the sort of field we touch on. And this is also a great motivation, you know, to have this diversity. I will take part into international conference and weather forecasting and new models, and then a conference in astronomy. And it's really cool to be in a diverse set of subject, not being at the forefront, but having a lot of other advantage, maybe, that result from the fact that, yeah, we are just, you know, the line behind the front line of researchers that do these discoveries.
I imagine that results in a lot of cross-pollination between different fields. I mean, people.
Same engineer, you know, he's assigned to work on that astronomy space mission, and then half of his week is assigned to another objective.
Should have said cross-pollination rather than pollinization. Okay, let's move on. So Joshua, you're the co-founder of T0 Technology. And what are the industrial benefits of space astronomy to Canada? I mean, as I said before, it's not just finding out interesting things in the universe. There are benefits, spin-offs. Can you elaborate on that, please?
Yeah, I think there's two ways to think about this. One is strictly in terms of technology, which is a pretty straightforward story, and one that we're used to telling ourselves from everything from how we structure R&D grants to how we structure commercialization programs, where we do all of this technology development for astrophysics, which tends to be on the bleeding edge of what's possible. And if you don't encourage that technology to be exported into the other areas where it's potentially useful, it won't be. The people working on it are focused on their goal of astrophysics, and so you do need some architecture, some policy around it to make sure that there's an incentive to look around at the work that you've done and, you know, see where else you can apply that, ideally here in Canada. The other aspect to that story is the talent pipeline. You know, working on especially space astronomy missions, they're long missions. Lightbird is I've been working on it for 10 years. We're not in phase 8 yet. It's going to be another 10-year mission, which means that there's already been 2 generations of graduate students that have, you know, come up through the Lightbird program, myself included. And so in a lot of ways, we're teaching people especially academics in these space missions, a lot more about industry than we probably realize, a lot more of the tools that are really useful for industry than are necessarily true in other academic pursuits. I mean, project management that Sarah mentioned is a great example. Being able to learn how to interface with the space agency, learn how to categorize technology risks, science risks, and advance all of this together is a pretty unique experience, even among large scientific collaborations. And so you have already mobilized a lot of graduate students learning all of these skills that are incredibly valuable outside of academia and outside of space astronomy. And most of those people aren't going to become professors. Most of them don't want to be. And so a lot of them will come up through, learn all of these skills that we give them in Canada, training them for the space missions and working with the CSA, and then look around and leave. And so that's part of the role of having, you know, a healthy group of technology companies that are already operating at that cutting edge, like ABB, like T0 Technology, where people who have these skills, it's just a half step off of that to being able to work still here in Canada, still on cutting edge technology and applying those skills instead of having to leave.
Yeah, excellent points. Thank you. I imagine that there's also these people could go off and do things that aren't even entirely due to space at all. They could be excited to do other things because they have this experience. So that I think is a very interesting driver as well. So any further thoughts from other panelists about that question? Nope. Okay, well, let's move on and talk about Sarah, what do you think the advantages are of space astronomy for successful international collaboration over those in, say, other sectors?
So we are very used to working in international collaborations, not just in space, but also on the ground. And part of it is because it's at the point where you know, an individual doing one project is not going to make a big you know, with their own instrument is not going to make much progress. And astronomy has been there for a long time. I think other fields are shifting into that mode now, where they realize that you just have to have large communities that come together to build next generation facilities. But we've been there for a long time. And so we've figured it out. And I think it's another, there's a, I guess a sociological component to this as well, that our community is very familiar with working in large collaborations because the next generation facilities we need are expensive. And so we have to have consensus about how we're going to spend our resources. We have a finite amount of resources in terms of money, but also in terms of people. So if we scatter everybody's interest too much, then we don't have enough resources to actually get the science out of these big projects that we want to do. So we've got to focus, we've got to prioritize. And we have to work collaboratively because it just takes a lot of person power to not only conceive and develop these new facilities, but then also to take advantage of them and use the data. And that's something that's quite unique to astronomy. When I was the science advisor at the CSA, I realized actually how different astronomy as a community is from some of the other space science communities. Because we need these big facilities and we have to come together both to develop them as well as to take advantage of them, we've been working in this communal mode for quite a long time. Astronomers, for example, are allergic to paying for software. Like, we refuse to do that. We expect everything to be open source. And that's actually quite different than a lot of other fields. And it's not just because we're cheap and you know, we don't want to buy software, but also we want to be able to trust it. And so if you're able to see what's under the hood, if things are open source, then that allows people to not only contribute to making it better and find bugs and check it, but also to validate their processes. So that's an aspect of the astronomy community that's really common. I think one thing that helps us a lot is actually right now we're in this era where there's so much data that it's not generally the case that I am worried that if I share my data, that somebody is going to scoop me. Because there's so many things that I could do. I have a lot of science questions. And so I don't worry about that in general. That is not true in other fields where people are concerned that if they share their data, somebody's going to steal their beautiful result before they have a chance to share it, you know, get credit for it. And we're just not in that regime. And so that's another thing that I think is unique about the community. I think other communities are going to get there, but right now we're sort of on this bleeding edge, and a lot of it has to do with our relationship to technology and just the requirement that that we need to work together both to share our resources and also to solve really hard problems.
Okay, what a great answer. Thank you, Sarah. Any further thoughts from Joshua or Fred about that? No? Okay, well, we're actually getting to the part of the Q&A. I don't know what the questions are. I have not been able to see what the questions might be. Now, we can continue with the moderated discussion if there aren't any other questions, but from the attendees. but I would like to ask the organizers to please launch a poll, which was asked, which will be posed to the participants. There you go. So please take a moment to answer these two questions, just for the benefit of the organizers, so they can have a better sense of who has attended this this session.
I think the vote is locked because it's written host and panelists cannot vote, at least on my display.
I thought that meant us, but the participants should be able to vote. I'm not sure if this is actually happening or not. I mean, I also got the window pop up as well. I can't fill in any of the answers, so it's gone. So hopefully the poll is done. Okay, so let's see, what questions do we have? Not able to vote. So okay, I think Chelsea, you might be a panelist because you're part of the you're not a participant. Anyhow, let's move on. Do we have a question from the Q&A? I don't have that available to me now. Is there should this have been in the webinar chat or a different place?
I can relate the question.
The Q&A, if you click on the Q&A button, there's a question.
Okay, great. Thank you. So anonymous attendee asks, what are Canada's unique strengths in astronomy that we could leverage to boost our economic growth? What do we do better than other countries? Great question. Who would like to take a stab at that?
I think Joshua and Fred could start, and then I can add something else if they if there's other things to add.
Okay.
Yeah, I think there probably is a good general answer to this question. I can provide some specific examples. So in the case of CMB astronomy, it's clear that Canada does better at this than anybody else, just in terms of our historical record, the different groups that are innovating on it, and our ability to translate that to industrial applications. We're first in the world for all of that. And the question of why is an interesting one. I think part of it has to do with being able to, at a policy level, when, for instance, the CSA decides what initiatives to select, being able to recognize the advancements and the strengths at the university and academic level. So there's a lot of technology and instrument development that happens at a university level. And there are processes like CASCA, which are really important to be able to filter up information to determine what are the things that we're consistently being selected to provide for, that we're consistently doing internationally in astronomy, being able to recognize that and then double down on it. And that's something that has happened very successfully for readout for superconducting detectors. And we've gotten a little bit lucky here as well, in the sense that another term for superconducting detectors is quantum sensors. And a lot of the technology development that's going into these types of sensors is also broadly applicable to superconducting quantum computing architectures. So all of these things kind of dovetailed with a hotspot in industry as well. And so we've been able to take that and leverage it in industry for superconducting devices in general. Now, we don't necessarily hit the jackpot with that on everything that we're good at in instrumentation in academia. But we really increase our probability of doing that if there are, big picture programs that can identify, small picture strengths and then be able to weight them with other projects like the CSA does. I'll hand it over to Fred now.
Now, I would try to say that it's not so much about what do we do better than the other country, is the fact that we train such expertise, such forefront worldwide, being at the forefront of technology that is important, being a part of all these detectors, fine mirrors that can find applications in a various domain it's having a good pool of people that do attend these international conferences and maintaining this momentum. These people then find jobs, I mean, in other parts of our industrial ecosystem. People at ABB, for instance, working on these space mission projects, they're pretty good picked by the headhunters because, you know, they have a good resume. They've worked with NASA on defending really challenging positions. So, of course, we can't offer all of our staff the position of engineering directors, but you know, some people, you know, climb up the ladder and are being chased to hold these positions at other industry. And so the fact that they were trained in this sort of environment, they have like a NASA tag to their resume, so to speak, is really, I think, helpful in order to elevate the industrial know-how, capacity, and you know, being world leader in many different aspects other than space astronomy.
Okay, excellent. I should clarify that CMB is the cosmic microwave background, just for those who aren't acronym literate. But yes, excellent answer.
Thanks, James.
Yes. Sarah, any further things to add?
Yes, I wanted to add one other point about where I think astronomy can make a really big contribution, and that's in the whole field of data. So data handling, data management, data distribution. So the big Canada is joined the Square Kilometer Array, which is one of those, it's a ground-based telescope, a radio telescope in South Africa and in Australia that just generates an unbelievable data rate. And so the and that just figuring out how to handle that data, how to analyze it, how to distribute it, it requires sophisticated cloud computing architecture, advanced algorithms, and so that's just going to be generally applicable for tons and tons of different fields. But astronomy has sort of a sweet spot, I think, because we have the advantage that we're actually looking at real things in the world. So we have an understanding of the laws of physics and the nature of the universe. So we are able to validate our processes because we have physical laws that underpin them. We don't have to worry about security in the same way that they do in other fields. The data about, you know, the first generation of galaxies in the universe is not sensitive. It's not going to put a nation's security at risk. So that's helpful also for thinking about figuring out how to analyze and manage these big data with sort of a safe data set. And also privacy is not a concern for the same reasons. We're looking at, I mean, I guess it's the privacy of baby galaxies, but we're not worried about people's health information, for example. So it's a really helpful sandbox, I think, in order to really develop algorithms, technologies, and protocols that can then be very, very broadly applicable. So I think I'll stop there. Thanks.
Okay, great. Let's move on to the next question by Ensia Arfani, who asks, how do you see the role of astronomy in achieving, I believe, the nation's sustainable development goals?
I can take that one if you want. So I'm here right now I'm in Montreal at a conference called Space for Women, which is about it's being co-organized by the Canadian Space Agency and the UN Committee on the Peaceful Use of Outer Space. And so space has in which space astronomy is a very important part, has a lot of very direct applications for the Sustainable Development Goals. So one is related to what Fred mentioned. So he talked about a satellite that they worked on, SciSat, which is measuring different molecules in the atmosphere. And so technologies that are developed for space astronomy, spectrographs that tell you what all the molecules are along the line of sight, are directly linked to following, for example, the Montreal Protocol, and seeing which things related to monitoring pollution, air quality, and also things related to climate change. So a lot of the technologies that are developed by astronomers who are really pushing the envelope can then be applied for these very concrete applications that are related to Sustainable Development Goals. Another application that I think is a little bit more indirect is because astronomy really functions in a lot of ways as kind of a gateway science. So there are lots of youth who get really excited about science when they're first introduced to astronomy. And so it's something that motivates them to continue in their studies. And even if they wind up doing something else, it can be that driver, that pull that gets them to study science and to attain higher education. And astronomy data also is free if you have the capability. There's a lot of publicly available data, and so anyone in the world can download James Webb Space Telescope data and look at it. And so that is something that you still, of course, need the resources to access it, but the data itself is free, and so that's an opportunity also for education that is quite exciting.
Fantastic answer. Anything you'd like to add, Fred or Joshua? No? Okay. Well, let's move on to the next question that has been posed to us. What do you think is the low-hanging fruit in terms of policy changes or research ecosystem changes that could help Canada take better advantage of our astronomy talent?
Like, I would like to start. I mean, we have to stay in these big international endeavors that are forefront in terms of technology development. We cannot be left behind, or I would hope that Canada, follows that. We were part of the James Webb. I think it would have been a big mistake if Canada said, no, we don't have the budget to get into James Webb, because, other nations would have made progress. The technology is constantly evolving, and if you don't follow, you are starting to lag behind. There's an analogy that is in cycling. When you cycle in a peloton, if you start to drag out and you lose the drive, and at a certain point, you're disconnected, and so you have to follow what the leading nations are involved in. When you take part in a project like that, you're exposed to all the technology elements that are done elsewhere around the world, and then you have access to the information. If you're not part of the project, you just do not attend the teleconference. You do not, see what others are developing, the nice ideas that, let's say, this company in the US did, this company in Italy did, and you're not exposed. And then there's much less opportunity for us, let's say, as a company, to respin these technology innovation in another bid. And there's increased risk that we will, be trying to compete on the world scene, and then one of our competitors, let's say in Europe, will say, oh, but I use this new process that was developed under James Webb, and then we have no idea about what this process is, and then let's say we lose the bid because we appear as less cutting edge than somebody else. So I encourage the government to keep, being on the lookout for these grand projects that are forefront in science and transformative, and bringing new technology that will find application after that, and ensure that Canada is part of these efforts. It's mandatory that we're part of one of these big 30-meter telescope if we want to stay in the game. I think Canada is based on exporting HQP. It's good that we have a resource, but we cannot have an economy that is solely on export of resource. We have the capacity to export, engineering, and we should be continuing on doing that.
Okay, great. Any further thoughts from the other panelists? Go ahead, Joshua.
Yeah, so Fred sort of addressed the big part of the funnel there in terms of what are the things we should be going after in terms of involvement in large projects. I can sort of address the totally opposite side of the funnel as well, which is what are the changes we might be able to make that increases the probability of doing that early technology and general sort of scientific development here in Canada that becomes that expertise that ends up having, economic or general significance for the astronomy community that leads us to be selected for missions. I think in general, instrumentation work is expensive, especially relative to theory work, observation work. The instrumentation departments in universities take up a lot of space. They require a lot of equipment, and it's fairly hard to encourage universities to make decisions that lead them to have like a number of instrumentation scientists developing different types of instrumentation in the same way that they might choose to expand departments in various other observation fields. And one of the powerful tools that Canada has to encourage that are some of the ways that like the RTI grants are structured, some of the ways that the NSERC grants for early career professors are structured. We can there's probably low-hanging fruit there to set aside money specifically for roles that would be instrumentation and technology development. And so in particular, some of the constraints on equipment costs for regular NSERC grants rule out a lot of technology development that might otherwise occur and be fully supported by those sorts of programs. The other thing is, there's a lot of people who are peers who spend their graduate studies working on instrumentation, doing engineering for physics or technology development for physics. And the jump from there to industry is really difficult to make unless you're jumping into somebody else's industry. And the MITAX, I will sing praises for MITAX all day long. The MITAX program to try to encourage entrepreneurship at a postdoctoral level is amazing. If we had more types of programs like that, which do two things, right? They do support with some money the continued technology development for the purpose of industrialization, but also they cut through a bunch of red tape associated with continuing to work in the university, who owns IP. All of this stuff is pre-negotiated through MITAX and the university. That just makes it easier for people like me to take what they've been doing that clearly has industrial applications and just do the extra like 4 steps. And I know that there's a lot of people in my same position that if those tools were more available, more people would use them for sure.
Okay, thank you, Joshua. Okay, so in the interest of time, I'd like to move on to the last question, which hopefully we can have a very short discussion on because we need to regrettably wrap up this panel by the end, by that bottom of the hour. So I'd just like to pose the final Q&A question, which is, are we transferring knowledge and technology to developing countries that host observatories?
So I can, I'll take the first stab at that. So I think there's one of the most remarkable examples of this is actually Chile. So Chile hosts many of the best ground-based observatories because of the amazing mountains that are there. So they're very high and they are very dry, which is something that astronomers are very fond of. So it's just geographically a fantastic place to put observatories. And the Chilean government has done a very good job in making sure that Chilean people actually are able to take advantage of the fact that they have this amazing resource. So as an example, Chilean astronomers typically get 10% of the telescope time on all the telescopes, or there's some, it may not be 10%, but there's some fraction of the telescope time of Chilean observatories that Chilean astronomers have access to. There are all of the people who work at the observatories, they're typically local, they're from Chile, not all of the people, but a lot of the telescope operators, a lot of the technicians, so a large fraction of the staff at all these observatories are local. And so there is it's created a whole ecosystem where they are trained locally. There are programs for training them so people can become telescope operators. Chilean astronomers are world class. They have access to fantastic resources. So I think that's an example where the country has really benefited and leveraged its geographic good luck to take advantage as a fantastic place for astronomy to really contribute to the economy.
Yeah, excellent. I think that's also mirrored in the southern states of Africa as well, due to the SKA as well. Okay, so thank you, Sarah. We will now move on to finish our panel. I would just like to ask the panel if they have any last thoughts that they would like to provide about the topics that we've discussed today. And if you have any closing remarks, I'd be happy to hear them. I'd like to open the floor to all of you to chime in here. Is there anything that we haven't covered that you would like to discuss in the remaining few minutes?
Well, I think it's just a fact that young kids, when you try to attract them to various fields of science, I mean, the astronomy is one that, you know, sticks, that people are passionate about the cosmos. You know, it somewhat relates us to God, or, you know, why is there something instead of nothing? This whole universe concept is beyond us. So it really you know, attracts the brightest, I think, students in the field, and that's something an interest we shall cultivate with these projects.
Thank you, Fred. Joshua, any last thoughts?
No, I don't have much to add, other than the fact that I think that there's a lot of things that we're currently doing right here to encourage a lot of the development that we're seeing, and the strengths that Canada has on the international stage, both in astronomy and in translating that to industry. So, you know, to some extent, I think the task falls to us to be able to recognize what we've been doing right in order to keep doing that right, and to you know, enhance that rather than kind of stray off that path. And so I'm happy to continue to participate in discussions like this that help us kind of get to the heart of why we have had the successes we've had and how to continue.
Okay, thank you, Joshua. And Sarah, any last thoughts that you would like to convey?
I'd just like to say I'm really grateful to be a part of this community, and to be able to be an astronomer, and to be an astronomer in Canada. And part of it is because I think we have this diversity of contributions to the field that makes it just a really fantastic and rewarding place to be.
Okay. All right, thank you very much. Okay, so in our remaining few minutes, I would very much like to thank everyone for attending today's pre-CSPC meeting. It was a very interesting panel. We had a lot of really good discussion, a lot of good feedback from the attendees. We would like to, well, thank you. We would like to ask the attendees to please fill out this particular feedback poll so that, again, the organizers can gather some data about your how you felt about this event and others related to the CSPC. So please go ahead and do that. Yes, I'd also like the audience to check out the CSPC website and the schedule for other very interesting panels and topics that will be discussed this week before the actual meeting, and of course next week during the actual meeting as well. And yes, I also think that, yeah, this has been a very, very informative and useful panel. I think Canadian astronomy has done very well in choosing the kinds of projects that it has become involved in. It certainly has maintained Canada's stature on the world stage for looking at the universe and providing impactful studies of the universe. We've done pretty well. We always would like to do better, and it's very healthy that we have I think the country is maturing to the point that we now have large-scale missions like Castor, for example, that Canada may lead. It's I think a very healthy development as well. So I think that yeah, we have a lot going on in our country, and this conversation that we've had today hopefully has given attendees a glimpse of the exciting things that are going on. Now, if people wanted to know more about Canadian astronomy and Canadian space astronomy, where would they go? How would they be able to find out about that? Does anyone have any ideas? Are there particular places that they recommend?
Well, the Canadian Space Agency certainly has information that's listed. If you're interested in Castor, castormission.org is a place, and the Long Range Plan, which is available from the Canadian Astronomical website, Astronomical Society's website. So yes, that tells you where we're going, what our priorities are, and also gives you information about the community overall.
It's an excellent read and a very well-developed document. So thanks for holding those copies up, Joshua. had them in hand.
Excellent reference material. Yeah. No, this document's I actually think it's a great introduction to Canada's space priorities, what we've already done, and who the teams are that are working on these things. It's a fantastic resource.
Yes, I agree. Okay, well, I believe that ends our panel. Thank you very much to the panelists for taking the time, especially you, Seraph, because you're already at another meeting who is and are multitasking to join this meeting. I really appreciate your expertise brought to this panel today. Thank you very much. And also thank you very much to the organizers for helping us discuss astronomy today. Have a great day, everyone, and enjoy the rest of the Canadian Space Policy or Science Policy Conference. Okay, bye, everyone.